Hi guys. Excuse me. So next installment here is going to be dealing with Chem Quest number 44 with our reaction rates, concentration, and time. So you guys have to recall from this particular Chem Quest is we're trying to identify the order of the reactant. In this case, NOCl, again, that's kind of a theme of this chapter. It's a good one to use for lots of these examples. But trying to identify its order when we don't have any corresponding rates, right? So on this table, you see we've got time and we've got a molarity, but we don't have a rate to compare those various molarities to identify the order, right? And so what we want to be able to do then is take this information and still identify that order for that reactant, okay? And there's a fairly simple way to do it. It looks fancy, but it's simple. It's pushing buttons on your calculator, writing some numbers down, and trying to identify which one, if you were to plot it on an XY scatter plot, gives you a straight line. And that's it. All right? So we're going to keep it simple. We're only going to deal with first and second order reactants. All right? And then our focus question today. So smart thing to do would be to have that Chem Quest 42. This is that last page, which you guys will turn in, all right, and we're going to focus on question number 1, and that goes all the way up through step H, all right. Some of these are real quick answers though, so it shouldn't be a super long video, all right. So here's our information. Now, what I want to do first, right, when I see a table like this is with these kinds of questions, we want to identify whether this is going to be a straight line as a first order reactant or a straight line as a second order reactant. All right, and that's what we're going to do. So all we're going to do is off to the side of this table, I'm going to write natural log of the molarity of NOCl, and then I'm going to post on this side 1 over the molarity of NOCl. All right. So if you recall from the rest of the Chem Quest, the natural log of this molarity right here would give us a straight line on the graph if the first order reactant. The inverse of that molarity will give us a straight line if it's a second order reactant. All right, so we're going to go ahead and just push our buttons on our calculator. So I'm going to go natural log 0.200, that gets me negative 1.61, right? Natural log 0.163, negative 1.81, and so on. And negative 2.14. Right? And I'm going to do likewise. I'm going to take the inverse of each of these numbers, so 1 over 0.200, and that gives me 5.00, and this gives me 6.13, this gives me 7.30, and then 8.47. Alright, so those numbers are there. So now let's just do some quick mental checking, right? If we're going to get a straight line, so you notice we've got a nice even interval for our time, right? So a quick way to check, we don't even have to make a graph in this case, right? Because only because our time interval is even, we want to look to see if we have an even interval between these numbers. If this number between here and here and here and here is even, and then there again, if that's even, is the same as the other intervals, that's going to give me a straight line, right? And then I'll cross-check that on this side as well. If these numbers, the difference between these numbers ends up being different, it won't be a straight line because this is an even interval here, uneven there, that means it won't be a straight line. All right? So we just do a quick difference check here, right? So my difference between 1.61 and 1.81 is 0.20, right? My difference between here and here is 0.18, and my difference between those two numbers is 0.15. All right, so I'm seeing a fairly significant difference. Not a super big change, but it is a difference. Now, keep in mind as we do these, that these numbers here are often rounded using sig figs and so on. So I may not get a perfect difference, right? But let's get the difference over here, and let's see which one is closer to that constant interval of difference, okay? So between 5 and 6.13, I've got a difference of 1.13. All right. Between 6.13 and 7.30 got a difference of 1.17. So that's not looking super consistent either. In fact, between those 2 points, this one looks better. But let's check one more down. 7.30, 8.47, that's a difference of 1.17. So again, we didn't end up with perfect results for either one of these, okay? But if you were to look at which one is more consistent in their difference between intervals, I would say the inverse relationship is a better indicator of what type of relationship that is, right? So I'm just going to go ahead and put a check next to this one, and we're going to know that that's second order, and we'll come back to that information a little bit later, right? So that inverse of the molarity gives a better or more consistent interval, and that would be, if I were to plot that, I would get something closer to a straight line here than I would if I used my natural log relationship, all right? Anyways, so let's go through some of the 1A through H here actual questions. So 1A, and this is a throwback to that initial ChemQuest 42. How does the rate of disappearance of NOCl compare to the rate of appearance of chlorine? Again, just go up here. The rates, remember, rates are always going to be mole ratio dependent, right? So NOCl versus chlorine gas, right? So disappearance of chlorine gas should be, or sorry, of NOCl. This is a disappearance, so it's a reactant, right? This is going to disappear at a rate double the rate at which chlorine gas forms, right? Because we have that 2-to-1 relationship. This one disappeared twice as fast as that one appears. All right. B, is this reaction first or second order with respect to NOCl? Right. So that's what we checked over here initially, right? I did that before I even started answering these questions because I knew that was something I'm going to have to do with things, right? Now we decided, because this gave me a more consistent interval, this is a second order reaction. So B would be second order. All right. C, it says to calculate the rate constant, K, and include units, right? So now we're going to imply some, some rate law stuff, okay? But with this case, remember I don't have any rates to use, right, to do my normal rate law, so I'm going to use that formula they gave me for second order reactants, right, which is that inverse, okay? So in this case, I'm going to, let's just pick this one right here at 1,000 seconds. All right, so I'm going to take this molarity as my comparison. So I'm going to go 1 over 0.137. This is letter C, by the way. Right, it's going to be equal to 1,000 K. So my time that corresponds with that molarity. K is my rate constant, which I will be solving for here shortly, plus 1 over 0.200, right? So again, what we did here, like if I was to give you the base formula, right? So I'm going to go 1 over molarity of reactant equals K, T for time, K for rate constant, plus 1 over molarity of reactant at 0 seconds, right? That's a little 0 there, right? So my molarity of my reactant at 0 seconds is 0.200. 1 over molarity reactant, I just chose one of them, right? And I just chose that one because I get to use 1,000, and that's the easiest number to divide by when I get to it. All right? So I just plug my numbers in, 1 over 0.137 times 1,000 times the rate constant plus 1 over 0.200, and I use this one, and this is the one I have to use in this case because that variable is always the molarity at 0 seconds. Okay? So now I just go back and solve for K in this case, right? So this would be 7.30 is equal to 1,000 K plus 5, right? So this would be 2.3 equals 1,000 times K. So K in this case would be equal to 0.0023, and that is my rate constant. All right, and there we have it. 0.0023 is my rate constant. That's my answer for letter C. Now, I'll be using that number again, and you can always bet on that, right? So I'm going to go ahead and write this up here, 0.0023 equals k. So I can come back with that with my other questions, and that way I can erase this as we go. All right. So letter D, it says what's the average rate of reaction time, rate of reaction between 0 and 1,000 seconds? All I'm going to do is calculate my average rate of disappearance, right? So I'm going to go change in molarity over change in time between 0 and 1,000 seconds, right? So my time interval will be 1,000 seconds. On the bottom, my change in molarity is 0.137 minus 0.200, right? 1,000 seconds. Right? When I do that, I get a negative number, but remember, with rates, we just take that negative away, and that gives me 6.3 times 10 to the negative fifth molarity per second. Now, that's an average, right? Our rate is actually changing over time because my reactant amount decreases, my rate's also going to decrease with it. So this is just an average rate over that time period. So at the beginning, it's probably faster than this. Toward the end of the interval, it's probably slower than that. All right? Anyways, so that was letter D, by the way. Part E. This video is going to get long here, but don't worry. Right? So, just describe how you find the instantaneous rate at 700 seconds using a plot of concentration versus time. Easy. X-axis is my time. Y-axis is these values right here. Right? I plot those points, draw my line through it, then I just find 720, make a line wherever this line, my plotted line, intersects that 720 seconds. There's my value for 720 or for 700 seconds, not 720. Pay attention, Mr. Hubert. All right. Anyways, that's a simple one. So rate law for this reaction. Now that I know my value for K, right, my rate constant, right, I've only got one reactant, so this makes it easy. So my rate, this is letter F, by the way. My rate law is going to be rate equals 0.0023 times 1 over molarity times seconds, right? I probably should have showed those units earlier. I apologize, but I don't want to redo this video just for that one little thing. But that's my units here, right? Times molarity of NOCl, right? And I need to raise that to a certain exponent, right? Because it's a second order reactant, that's going to be a 2. And that's my rate law. So now I can figure out my rate at various molarities because now I know my rate constant, which I figured out by going through all this mess. Okay? So, nearing the end here, letter G. This is going to be multi-step problem here. All right? So, I'm going to leave that formula up there just so I can refer back to it. Put my letter G down here. It says, okay, calculate the rate of disappearance of NOCl at time equals 1550 seconds. Right? So, I'm going to have to figure out this rate, but what I need to figure out first is my molarity at 1,550 seconds. All right? So what I'm going to do is I'm going to use my inverse rule here, right, to figure out my molarity, and then plug that molarity in there when I'm ready. All right? So, but I don't know, so I'm going to go my 1 over x. So I don't know my molarity at 1,550 seconds yet. It's going to be equal to 1,550 times 0.0023. So this is my time times my rate constant, right? I do know what time I'm looking for, I just don't know that molarity yet. Okay? Plus 1 over 0.200, right? And I know this value because this is my molarity of my reactant at 0 seconds, right? So when I solve for that, I do get x equals 0.117 molarity. Right, so now that I know my molarity, I can plug that value in here. Okay, so I'm going to erase this just so I have space. This is 0.117 so I don't forget. So I'm going to go rate equals 0.0023 times 1 over molarity times seconds times 0.117 molarity squared. Alright, I go through that mess right there, and what I end up with is my rate is equal to 3.15 times 10 to the negative fifth molarity per second. Alright, and do remember that your rate for these types of problems is always going to be molarity over seconds. Alright? So, one more problem, and we're going to do this one just like we did the last one. So that was letter G, by the way, in case you can't remember, right? So letter H, last but not least here. I'm going to leave that formula up there. Alright, I'm going to solve it in the same way, except I'm going to do my rate of appearance of chlorine gas. Now, in this case, I'm going to add one more step in between, which is my mole ratio, but we'll get to that in a second. So let's figure out my molarity of NaCl at 750 seconds. Once I know that, I can know my molarity of chlorine gas. Alright? So, again, my inverse relationship here, because this is a second order reactant, I'm going to go 1 over x again equals 750, which is my time, 750 seconds, times 0.0023 plus 1 over 0.200. Alright, and in this case, when I solve for x, I should get 0.149 molarity, right? Now, that's the molarity of what? Of NaCl. Alright, so I know that molarity, I just use my mole ratio to get my chlorine. So, my chlorine gas moles should be half of that. Alright, and what I should get in that case, well, actually, let's do this. Let's do my rate first, and then do my mole ratio last. Let's do that. So let's get my rate of disappearance of NaCl at that point. Then we'll come back and do that mole ratio issue. All right. So we're at 0.149 there, so I don't forget that number. Let me go rate equals 0.0023 times 1 over moles times seconds times 0.149 molarity squared, right? And when I get that, I should get 5.10 times 10 to the negative fifth, right? And what am I going to do with that number? I'm just going to cut it in half, right? So take that, divide it by 2, and that is going to give me 2.55 times 10 to the negative fifth, right? Molarity per second, and that's for chlorine gas. Done. So, sorry, this is like an 18.5-minute video. My apologies, but hopefully when you're working on this stuff at home or even in class, pulling it up on your phone, it's helpful. Adios.